In this presentation, I'm going to talk about harmonic balance analysis of nonlinear RF circuits. This is the most popular technique for simulating RF circuits. And what we're doing in this technique, and this is what makes it unique, is that we're solving for the steady state of the circuit. We are solving for the steady state response of the circuit. We are not looking at the transient response, the type of response that you would see when you turn the circuit on, the type of response that you would see when the circuit is operating in a pulsed mode, because of course in an RF communication system the system is not operating all the time, it is not transmitting all of the time. One of the prices that we pay for only looking at the steady state response of a system and not the transient response is that we need to make approximations for the signal, and we cannot look at actual real-world signals. We look at signals which we hope represent the behavior of a circuit with an actual digitally modulated signal. So harmonic balance is one of several techniques for analyzing the steady state response of a circuit, and the key feature is that we assume that the signal can be modeled as the sum of discrete tones. That is, we're solving for the phases of these tones in the circuit, and so we are assuming a steady state situation. Can all signals be represented by a sum of discrete tones? Well, very few real-world signals can be represented that way. But you know what? When we're in the lab, we do most of our measurements using discrete tones. We may apply a single sinusoid to a linear circuit and sweep that single sinusoid with frequency to get the linear response of the circuit, the linear steady-state response in the frequency domain. We also do two-tone testing in the lab. We can do the single-tone testing and the two-tone testing in simulation, either for a purely linear circuit or a circuit with nonlinear elements. Now we can solve for the phases of the discrete tones that we're using to represent our actual real-world signal. We can solve for the phases everywhere, or we can solve for the phases just at the nonlinear elements. When you look at an RF circuit, you see that there are a very large number of linear elements and usually very few nonlinear elements. Maybe a few diodes, maybe a few transistors. And if we assume the steady state, we can take all of the linear elements together and we can combine their response. We can take all the linear elements and determine their overall response at each of the discrete tones. So one of the reasons why the harmonic balance method is so effective is that we only need to solve for the phases at the nonlinear elements and not everywhere. If we wanted to, we could force a solution everywhere. Perhaps we want to know an exact voltage at a particular point in the middle of a linear circuit, but rarely do we actually do that. The big caveat here, the note, is that we cannot consider actual digitally modulated signals. So when we are approximating our digitally modulated signal, perhaps using a two-tone test, that is, we're modeling the digitally modulated signal as though it's just two tones, we are hoping that we obtain simulation results that are a good representation of how our circuit behaves. It turns out that there is a theory that says that if we use a very large number of discrete tones, let's say 10 or 20, we actually get the statistics of our circuit fairly accurately, and those statistics enable us to really understand what is happening with the digitally modulated signals. Unfortunately, considering 10 discrete tones that are not harmonically related is a little bit too complex. So when we're considering a sum of discrete tones, we could consider in one case that we have a fundamental in the harmonics, or we could consider a more complicated case where we have two tones and their harmonics and their intermodulation products. We could get up to 3 tones or 4 tones, but getting up to 10 or 20 tones is a little bit beyond what is reasonable today. But you could think that 5 or 10 years out we could realistically do that. So there will be some inaccuracies in the results that we obtain through harmonic balance simulation, but you know what, there are so many things that we can't model very accurately that we always go into the lab and do experimental work in any case. So even if our simulation is out by a few percent, we will catch the results in that final laboratory-based optimization. So here is our modeling problem. We really have two modeling problems when we're trying to analyze nonlinear RF circuits. We can simplify things by just considering a resistor as shown on the left-hand side. Now this is called a resistor with a passive convention. So we have a voltage across the resistor here. See the positive side and the negative side of the voltage, and when they have the current flowing through it. For a linear resistor, this is our characteristic. The relationship between the instantaneous current and the instantaneous voltage is a straight line. So if we apply a sinusoid at a single frequency as our input, we will have a sinusoid at the same frequency at the output, and there will be no harmonic content. But consider a nonlinear characteristic, in this case a diode. So a diode has an exponential relationship between the current and the voltage. This current is an exponential of the voltage, and so if we apply a single sinusoid as the input voltage, we will have an output here that includes harmonics. Now if we applied a signal to the input that consisted of two sinusoids, the output will consist of a signal which consists of those original two discrete tones plus the harmonics of those tones plus the intermodulation frequencies of those two tones. That is, all integer sum and difference frequencies of those two tones. There are some particular characteristics of the RF signals that we will be using to drive our RF circuit. In general, we will be dealing with modulated signals with very narrow modulation bandwidth. For example, a 5 MHz wideband CDMA signal on a 2 GHz carrier. So the carrier is a sinusoid varying at the rate of 2 GHz. It has a period of half a nanosecond, but the information content on that carrier is all within this 5 MHz bandwidth. That is, we will have a symbol that changes state at the rate of 5 megasamples per second. So it takes 1/5 of a microsecond for the symbol to go from one point to another. So you can imagine that we can get a reasonably good estimate of what is happening by solving for the state of the circuit at 2 GHz, then solving for the state of the circuit at perhaps 2 and a bit gigahertz, up to the point where we get to 2.005 gigahertz. Another way of approximating what is happening is to consider that we have a 2 gigahertz signal with a number of discrete sidebands that go out to 5 megahertz on either side of our carrier. If we limited the modulation sideband to just one tone, well, that's an approximation. But the information in a carrier with a single sideband is not the same as the information in a carrier that is modulated by a wideband CDMA signal. The information certainly is not there, but perhaps it does indicate what is going on. It turns out that a better approximation, if we really need to have a simple approximation, for a 2 GHz carrier with a 5 MHz wideband CDMA modulation on it is to consider two discrete tones that are within 5 MHz of each other. An even better one would be to consider three discrete tones that are spread out over that 5 MHz. And there have been a number of papers written that show that that is a reasonable approximation. Now, some of the things that we are particularly avoiding are situations like this. When we have a biased circuit, it takes a long time to reach steady state. It could take billions of cycles of our carrier before we reach steady state. That is a lot to try and simulate. So by focusing on the steady state response, we are deliberately ignoring this bias circuit setup. Also, when we're doing simulation of RF circuits, we need the dynamic range of our simulation. Of course, there are many ways that we could define dynamic range. A good metric is our ability to detect a small signal at one frequency in the presence of a large signal that's only a little bit away. In communication systems, we need a simulation dynamic range which is about 20 dB better than our specifications require. In wideband CDMA, the dynamic range we require of our nonlinear RF circuits is about 80 dB. That is, we must not generate spurious signals that are more than 80 dB below the carrier, below the signal that we intend to radiate. Simulation needs to be 20 dB, so we need a simulation dynamic range of about 100 dB. That is realistically beyond the capability of commercial SPICE simulators. So even though a SPICE simulator would take a very long time to reach the steady state situation that we're interested in, even then it would not enable us to resolve very small signals. In radar, we need a simulation dynamic range of 160 dB, so the situation is even worse. Harmonic balance easily achieves dynamic ranges of 200 dB. So the simulation dynamic range of harmonic balance simulators is certainly sufficient to resolve small signals in the presence of large signals. And it does it very quickly. The problem is, the fundamental problem is, that we cannot look at completely realistic signals. So let's just go over why we do not want to do transient simulation of RF circuits. Actually, we would really like to do them, but it's simply not practical. And the main reason is that it takes a very long time to simulate meaningful distortion metrics. So we are interested in adjacent channel power ratio. We're interested in the signal that we dump in the neighboring communication channel. If we do the transient simulation of our sample signal here, a 5 MHz wideband CDMA signal on a 2 GHz carrier, we would need to consider a time step for the simulation that is much shorter than the period of the 2 GHz carrier. So the period of the 2 GHz signal is 500 picoseconds. Then we need a delta t, which is less than 25 picoseconds. That is this time step. Usually, however, we find that that time step needs to be about a picosecond. And that is driven by that exponential current voltage characteristic that, say, occurs at the base for a BJT or occurs because of the parasitic effects in a MOSFET. Now our symbol interval is 200 nanoseconds. That's 1/5 of a microsecond. So to look at meaningful signal distortion statistics would require us to look at almost a millisecond of simulation, and we're stepping at picoseconds. So you can see that we're talking about millions of time points, billions of time points, actually trillions of time points. And then when we're considering dynamic range of at least 100 dB, we may need to even simulate longer. We will have to wait for our transients to settle out to the point where the transients are no longer affecting our dynamic range. No one has been able to do a transient simulation of an RF circuit with a realistic signal and obtain the metrics that we really need. Bias circuits take a long time, of course, and the bottom line is it's just not practical to do this. When it comes to modeling nonlinear microwave circuits, there are two commercially available approaches, and the harmonic balance method is just one. In the harmonic balance method, we assume that the signals in a circuit are of sum of sinusoids, and each of those sinusoids could have any amplitude we want. And the reason why harmonic balance works so well for a large number of RF circuits is that many of our RF circuits, especially our microwave circuits, consist of a large number of linear elements, but very few nonlinear elements. That is, few transistors, few diodes. In fact, the ratio could be as much as 1,000 to 1. We could have 1,000 linear elements for each nonlinear element. When we're operating harmonic balance, we decide to separate or partition our linear elements into one block and our nonlinear elements into another. Since we are dealing with a fixed number of phases, a fixed number of sinusoids at fixed frequency, we can characterize the external characteristics of the linear circuit using their S parameters or Y parameters. We do not need to solve every bit of the linear circuit over and over again. In fact, we only need to solve it once up front, store the Y parameters of that whole linear circuit, but only at the interface points with the nonlinear circuit. With the nonlinear elements, we will have to consider them at every iteration in our analysis. So harmonic balance works extremely well when we have a large number of linear elements and few nonlinear elements. An alternative analysis technique is the PSS technique, or the periodic steady state simulation. This is SPICE-based. In periodic steady state simulation, we are assuming the steady state, which means that at every point in our circuit, and in the case of inductors and capacitors, we're considering the state variables for those as well, we are assuming that there is a phasor at a single frequency for each of them. There will also be harmonics. Then at the start of a period, we know what the voltages and the state variables will be at the start of that period. We simulate our circuit in traditional SPICE for one period of our fundamental tone, and ideally the value of the voltages and the state variables at the end of the period are exactly the same as the values we assumed at the beginning. If they're not, we will update our guess for the phases and we'll do the simulation again. This works very well, but of course we have a single sinusoid, which can be quite large. Then when we have that solution, we're in a position where we can determine the dynamic state of the circuit. And that dynamic state is represented as a conversion matrix. We assume that that carrier is modulated at a much lower level. Now, periodic steady state simulation is not nearly as efficient as harmonic balance simulation for traditional microwave circuits with just a few nonlinear elements. When we move onto an RFIC, however, things are different. There are very few linear elements and a very large number of nonlinear elements. In that case, periodic steady state simulation can work fairly well, or comparably to a harmonic balance. When we get up to a very large number of nonlinear elements, harmonic balance really slows down quite a lot. However, with harmonic balance simulation, we can look at more realistic signals. We can look at signals that have, say, two large non-harmonically related tones. In periodic steady state simulation, we must represent all of our signals as one tone and perhaps its harmonics with a low level modulation superimposed on top of it. Periodic steady state simulation is used in some commercial tools, and it has the advantage that we are using the actual transistor models that we would use in transient simulation. In harmonic balance simulation, at least the commercially available versions of harmonic balance simulation, we have to rewrite, of course the user doesn't have to rewrite, but the models for the transistors are much harder to develop, and they cannot be in the same form as they are in the transient simulation. These are two different approaches, but many large design houses will simulate their circuits, especially RFIC circuits, both ways. And if there's a discrepancy, they try and understand why there's a discrepancy. And often that discrepancy occurs because there's some extra sensitivity in the circuit that was not anticipated up front. So if you're doing an RFIC and you're investing maybe $100 million in the whole design effort, it's a reasonable thing to expect that you will simulate the circuit both ways. But today we're going to focus on harmonic balance simulation. So here is the harmonic balance approach. we're going to assume that the signals in the circuit are a sum of sinusoids, and we're going to partition the circuit into two subcircuits, a linear subcircuit and a nonlinear subcircuit. Right up front, we're going to use a linear simulation of the linear subcircuit to obtain the Y parameters of the circuit, referenced to just all the external terminals. We don't worry about what's happening internally. And at these terminals, one here, 2, 3, we're going to assume that the signal can be represented by phases. So we can express these as voltages V1, V2, etc. Then, assuming a voltage, let's take V1, assuming the voltage phasor here, we calculate the current flowing into the linear circuit. All we have to do is multiply out the Y parameter matrix, and then we do a nonlinear simulation to calculate the currents flowing into the nonlinear circuit. So that's a key idea. We separate linear elements into a subcircuit, we separate the nonlinear elements off into a subcircuit, and in a simulator every element is tagged as to whether it's linear or nonlinear. So the simulator can handle all of this partitioning automatically. We do not have to do it. So let's look at an example, a fairly simple example, so we get an idea of how harmonic balance actually works. Here is the circuit. We have a nonlinear element on the right here, and the nonlinear element is going to be described by this equation, so a simple quadratic. Can't imagine things being much simpler than this. Our linear circuit consists of a 1 ohm resistor and a voltage source. So our first step is going to be to partition the circuit into a linear subcircuit and a nonlinear subcircuit. We then have to assume the form of the signals at the interface. Now I'm just showing the voltage here. So at this interface, I am going to assume that the voltage, V of t, comprises 3 discrete tones. One of them is just DC. Well, we will consider DC as a tone. One of them is a signal at the fundamental. It has a magnitude V1, and things can be kept fairly simple here. We can leave out phase. But there is another signal which is at the second harmonic. I have a similar description for the linear current. It'll be comprised of 3 discrete tones, and a similar description for the nonlinear current. It will consist of 3 discrete tones. My next step inside the simulator, and I wrote this all in MATLAB, so these equations pretty much go directly into MATLAB. I then write a description of the circuit behavior in terms of phases, and here's the description of the relationship between the currents and the voltages in terms of discrete phases, and these phases are just scalars here because I've left out the phase. As far as the linear circuit goes, there is a source which is at the fundamental, omega. As far as the DC current goes, it only depends on V0 because that voltage source, E, looks like a short circuit at DC. At the fundamental, the linear current is equal to V1, the voltage phasor at frequency 1 at the interface, less the voltage source, and at the second harmonic, 2 omega, the voltage source looks like a short circuit, so the linear current is just equal to the linear voltage, and they're directly equal to each other because RS is just 1 ohm. I've kept things as simple as possible. Now when we go over to the nonlinear circuit, remember that our nonlinearity is described by this quadratic. So I would substitute for V of t with these 3 discrete tones, V0, V1, V2. So I substitute for Vt into my expression. I expand it out trigonometrically. I then group the current components in terms of their phases, and this is what I end up with over here. The linear current at DC, I0, is equal to V0 plus a half V2 squared, so it's the rectified version. Our nonlinear current at I1 is just V1 when I do the trigonometric expansion, and the nonlinear current at I2 is just equal to a half V1 squared. Now you may note that when I drop V2 into this quadratic term, I will generate some DC. I'll also generate a signal component at 4 omega. But in the harmonic balance method, we have to choose the number of discrete tones we're going to retain. 4 omega is not one of those tones that we retain, so we just drop it off. And that's the main source of error in the harmonic balance method. Tones such as 4 omega in this case and other tones are simply not considered. We must limit the number of tones that we have. And at the top here I'm just summarizing where we were. We partitioned our circuit into linear and nonlinear subcircuits, and these are the voltages and currents that describe the phasor relationship in that circuit. Now KCl is used as a measure of error because of course the linear currents must be balanced by the nonlinear currents. We express our KCl error as this. We have a KCl error capital F that is made up of 3 component KCl errors, and we'll just keep the magnitude of those KCl errors. F0 is the KCl error contribution at DC. So we take the DC current flowing into the linear subcircuit, compare that to the nonlinear current, and I0 bar and I0 in opposite directions, so we just add them together to get our KCl error. We do a similar thing at the fundamental at omega, and again we do it at 2 omega. So now we have an error measure. We have the relationship between the currents and voltages. We need to iterate on our voltage guesses, that is V0, V1 and V2, to take the error to 0. And the way to do that is to use the Newton iteration. So we want to update our voltage guess. So our voltage guess is V0, V1, V2 expressed as a vector here. This is the I plus 1th iterate of the voltages, which is equal to the ith iterate of the voltages, corrected by this term here. So this is our error vector, and this matrix here, so this whole thing is a matrix, and is, that's the matrix there, that's called the Jacobian matrix, and that is the derivative of the error of the KCl error of the current with respect to V. So expand things out a little bit more. This is what our iteration is, and this is what the Jacobian looks like. So it's the Jacobian of the ith iterate of the voltages. This is just transpose here, which enables the column vector to be written in a more compact row vector form. Just look at the first element here. What this first element is saying, it is the partial derivative of F0, that is the KCl error at DC, with respect to the phasor at DC. If we pick an element that's off the diagonal, here we have the partial derivative of the KCl error at frequency 1, which is our fundamental, with respect to the phasor of our second harmonic. So we take our Jacobian, we invert it, and that's saying that given this error and the error at the other tones, multiplying that vector by the inverse of our Jacobian tells us how much we have to update the voltage to get rid of the error completely. All of this, of course, is handled automatically in a large commercial program. There's a lot of coding that goes behind this, and it is surprising how well these Newton iterations work. Well, really, most of our circuits are designed to be linear circuits, and then the nonlinear behavior is a departure from linearity. Our amplifiers, even our power amplifiers, are designed with the view that they're essentially linear circuits that depart from linearity. So harmonic balance works very well for RF nonlinear circuits. So let's just consider the error at the second harmonic. So our error is F2. This is the KCl error at the second harmonic, and it is the sum of the linear current and the nonlinear current. Adding them together should give us a KCl error that is 0 if they're equal to each other. Now we need the derivative of F2 with respect to each of the voltage phases. So let's pick one. So the derivative of F2 with respect to V1 is made up of a component that comes from the nonlinear current and a component that comes from the linear current. Now we know some things about this up front. One is that the derivative of the current at the second harmonic with respect to the voltage at the fundamental must be 0. It's a linear circuit. Only the voltage at a particular frequency can affect the current at that frequency. When we look at the second harmonic of the nonlinear current, this is the expression that we derived earlier from trigonometric considerations, we see that I2 is equal to 1/2 times V1 squared. So we can get the derivative of that, di2 dV1. We go through the derivative experience and we end up with the derivative being equal to, in this case, just a fairly simple expression. These derivatives in all commercial code are developed manually and they're incorporated in the transistor model or the diode model. So writing these models is a very laborious exercise, with the result that there are not a lot of different types of models in the simulators. In fact, that's one of our big research problems going out, is how can we come up with models much faster instead of spending 2 or 3 years developing the model that we can use in a harmonic balance simulator. It's much faster to develop a model that will be used in a SPICE-like simulator. So this slide just shows us one of the partial derivative entries to go into the Jacobian. Similarly, we can develop the other entries into the Jacobian matrix. And so I wrote a MATLAB code, as I said. I just wrote these in directly. I said that this entry, which is the 1,1 entry of the Jacobian, is just equal to that. The 1,2 entry is just equal to, well, this one here, etc. It's a very simple piece of code. I just have to calculate each of the Jacobian entries manually. So now we have enough equations to solve the Newton iteration, and this is the full Newton iteration, and it works surprisingly well. Here is our circuit again partitioned into linear and nonlinear subcircuits, and here are the results of my iterations. Iteration 0, well, I just have to guess things, don't I? The best I can do is to make a guess for the voltages at the interface. The only independent source here is E, which is set to 1 volt. So my initial guess for the DC voltage, V0, is 0. My initial guess for V1, well, I know that if I linearize the nonlinear circuit, it will look like just a 1 ohm resistor. So it's as though I have a voltage divider here. So my initial guess for V1 is 0.5. My initial guess for V2 is 0. My first iteration, I calculate the nonlinear currents. So I have the formulas for the phasor values of the currents at DC, the fundamental and the second harmonic, and I see I actually do get values for the nonlinear current at DC, nonlinear current at the fundamental and at the second harmonic. In my next iteration, I'm going to calculate the current into the linear circuit. So there's my current into the linear circuit at the fundamental, and I will update my voltage guesses given the currents that are flowing, and I calculate the nonlinear currents. And then I do this iteration over and over again. What I call the 0th iteration or the first iteration could be up to some interpretation. But here I'm going to say that I'm going to calculate the linear currents, then the voltages, and then the nonlinear currents, and that defines an iteration. Now if you look through here, when we get to iteration 7, we've got to steady state. Things are not changing. Compare the values at the 6th iteration to the values at the 7th iteration. Let's just pick one. Let's pick the DC voltage. Although what we will be doing in the program is that we will compare each of our phases, usually the voltage phases, at one iteration to what we obtained at the previous iteration. If the change is below a certain threshold, we'll say we've obtained an answer. Well, you compare the 7th iteration for the DC voltage to the 6th iteration for the DC voltage, and we see that they're accurate to 1, 2, 3, 4, 5, 6 significant digits. In fact, if we go back to the 5th iteration, we see that we've obtained the same value, 4th the same value, but some of the other values haven't quite settled down. Usually with harmonic balance analysis, we find that we obtain a stable solution after just 3 or 4 iterations. It is surprising how fast harmonic balance converges. Of course, as a user, we do not see that. If there is a problem, and it takes many iterations to try and get a steady state solution, that's usually an indication that there is a programming error in the model itself, in that we haven't got the model errors correct. Now, using harmonic balance analysis requires a little bit of extra input from the user. There are a number of default decisions that have been made, but of course, as an engineer, we know that we are always going to be pushing things to where they're about to break, and we need to know how to go forward. In a very large company, there will be a group of experts who really know how the simulator works, and they'll know what to do if problems arise. In other cases, if you're a big user, you'll find that you have access to an application engineer, and you'll call the application engineer up if you have problems. In fact, that's why you pay so much for some of these tools, is to be able to talk to somebody on the phone. There are 3 major factors that limit the accuracy of harmonic balance. One of these is the number of tones included in the analysis. Now, it turns out that many of the circuits that different people look at are very similar. So we're often looking at amplifiers or mixers. Once you have made a decision as to the number of tones you need for a particular type of amplifier, you may not have to make a change to that decision in years. You just keep on going. But limiting the number of tones included in the analysis affects the accuracy. Another problem, which seems to be related, are the aliasing errors that are due to a finite transform spectrum. This error can be reduced by considering many tones. In fact, by considering many tones, we're saying that the tones that we're not considering are negligible, virtually zero. We can leave them out. The aliasing error is not quite the same as not having enough tones to accurately represent the signal. The aliasing errors are a numerically introduced error. This sets an upper limit on resolution most of the time. Another major limiting factor is the final value of the harmonic balance error that we're able to achieve. It will never be exactly zero, of course. In fact, you can never get zero from Newton iteration. There must always be a little error, and we'll always be making corrections, and there'll be a little bit of dithering. But sometimes there's a final error because our equations are not good enough. And the major limiting factor here is how closely the Jacobian describes the actual error function. Or, put it another way, how accurately the derivatives of our current with respect to voltage describe the way that the current varies with respect to voltage. Are our derivatives exact? Very, very difficult to get our derivatives to be exactly right. So in summarizing here, there are really 2 big issues. One is, have we considered enough tones? We can check that by every now and again considering more tones in our simulation and seeing if there's a difference in the error. And the other one is realizing that if we can never get our error to go to zero, it is almost certainly due to the inaccuracies in the transistor models. And some of you will end up having to develop your own models. If you're trying to do a competitive design, there is a chance that you're going to be using transistors that no one else has used. And since it takes 2-3 years to develop a transistor model, very often you're going to be dealing with situations where the model has not been developed by others. Your company, your organization has a competitive advantage by getting in there first. And there are companies that you can also contract to develop models. So lots of decisions need to be made there. But in the end, we go to the lab. Any errors here we can fix sometimes in the lab. Periodic steady state analysis is the other technique that is used to simulate nonlinear RF circuits. And this is particularly well suited for looking at RFICs. So the key here is that, or the outline of how the method works, is that we use a spice-like analysis for one period of a large tone. From that, we develop a linearized dynamic circuit. We use something equivalent to a conversion matrix to do that. And the other tones that are not harmonically related to that tone, we consider as operating on the dynamic circuit. So this is a restriction on our ability to model realistic signals. It turns out, as I said before, that a reasonably good model for a digitally modulated signal is to consider a large number of non-harmonically related discrete tones, such as, say, 20 tones. Well, here's a little bit more detail. Just as we did with harmonic balance, when we're doing our nonlinear simulation, we guess the initial voltages at all terminals in our circuit, so we do not partition our circuit into linear and nonlinear parts. In fact, that's a bit of a fruitless exercise when we're on an RFIC because everything looks as though it's nonlinear. So as well as guessing all the voltages at the terminals, we need to guess the state variables for capacitors and inductors as well. Then we simulate the circuit using transient analysis for one period of the exciting waveform, and the state variables are updated if required. The solution, this is the dynamic circuit model that we come up with, is akin to a conversion matrix. As I said before, the advantage of the PSS technique is first that we can use a conventional SPICE simulator, which would be used in designing digital circuits. And so there's a much broader base to support transistor model development than just the RF circuits. So summarizing things here, the analysis is based on assuming a finite number of tones. Our signal that we are modeling, the signal that we are simulating with, is not the same as a digitally modulated signal. There will be errors. We must go into the lab later on. And a fundamental idea is that we partition our circuit into linear and nonlinear parts.